Hello and welcome to Brahma's Notes. This is the second video on electrolysis, and we are going to basically look at the terms in electrolysis. The first two terms we shall deal with are conductors and non-conductors. So what are conductors? A substance which can allow electric current to pass through it is called a conductor. So if you have your metallic rod and electricity can pass through it, then that metallic rod is a conductor. So all metals, because they have free or delocalized electrons, they will be conductors. Maybe carbon, it's a non-metal, but we shall have to be specific. Carbon in form of graphite is also a conductor because electricity can pass through it. So that's a conductor. However, non-conductors, just that will mean the opposite of conductors, and they are also known as insulators. So these are substances that do not allow electricity to pass through. And some examples can include rubber, plastic, wood, etc. So we shall get used to conductors and non-conductors as we proceed. The second term we are going to look at electrolytes and non-electrolytes. Now, electrolytes are compounds which, when in solution or molten form, conduct electricity, and they tend to be decomposed or broken by it. What do we mean by that? We shall see what we mean by decomposed by it. So we shall see that electrolytes will actually be conductors because they will have to conduct electricity, but on two conditions. If at all they are in solution form, that is to say aqueous when dissolved in water, or they are in molten form, that is to say if we melt them and they are in liquid form but no water present. Then we shall see what we mean by decomposed by it. So some examples of electrolytes can include molten ionic compounds. I'll still stick to our simple version of ionic compounds, and that is sodium chloride. So molten sodium chloride will be sodium chloride in liquid form. This is an electrolyte, and it can conduct electricity and be broken by it. Then we can have aqueous solutions of ionic compounds. Okay, in this case, let's go for our potassium chloride. We shall try to keep it simple, but in this case aqueous, meaning there is some water content present. So whenever we pass electricity through these solutions, not only will this electricity pass through them, but it will decompose them. To decompose is to break, to compose is to bring together. So this potassium chloride will be broken down, as we shall see later on, in two different substances. So that will be the effect of electricity. So an electrolyte is a compound which, when in solution or molten form, conducts electricity and is decomposed by it. Take note, we can't have an electrolyte in solid form. So we shall mainly be dealing with liquids or solutions. NB. All electrolytes are ionic compounds. We shall see why they are ionic compounds. Obviously, it's because in solution or in liquid form, it's ions which will conduct electricity. So they have to be composed of ions. The above compounds only conduct electricity in molten, sometimes it's called fused, and aqueous state. At least we have already emphasized that. And they do not, I repeat, they do not conduct electricity in solid state. Remember, in solid state, the ions present in these ionic compounds are strongly attached to one another, that they can't be free to move around and conduct electricity. So in solid state, they will not be able to conduct electricity because they can't move around. Reason: in solid state, the ions are rigidly held in regular positions by the strong forces, as such are unable to move freely. When you look at our sodium chloride, overall charge is 0, but still within the sodium chloride, when it's being formed, it's ionic in nature. So the force of attraction between these two in solid form is so strong that this will always be a unit in solid form, and the sodium ions are not free to move around, just like the negatively charged ions as well. However, in molten and aqueous state, ions are free to move, hence conducting electricity. So whenever we are in aqueous state, that is to say when we dissolve these ionic compounds in water or we melt them, then these ions will always be free to move. They will always be free to roam around because they are apart. They have been pulled apart either by the water molecules or by the temperature of that molten state. The passage of electricity through the electrolyte is accompanied by a chemical decomposition. I already talked about the breakdown. Decomposition means breakdown, and I am still emphasizing we shall see what we mean by accompanied by a breakdown. So not only does electricity pass through our sodium chloride solution, but it will also break it down. The decomposition of an electrolyte when electric current passes through it will be called electrolysis. Electrolysis. Basically, we are breaking down the electrolyte. Electrolyte, then lysis. So electrolyte and lysis means breakdown or splitting. So electrolysis is basically the breakdown of an electrolyte when we pass electricity through it. Secondly, we have a non-electrolyte, and just like non-conductor, it will be a compound which when in aqueous or molten does not conduct electricity. So you have a substance, you have dissolved it in water, or you have tried to melt it into its liquid form, but still does not conduct electricity. For example, alcohol, say ethanol. When you look at ethanol, it's a liquid. You might be like, why isn't it conducting electricity? Because it is an electrolyte. Dissolve your sugar in water so that you get your sugar solution. Dip your graphite rods, attach your crocodile clips, still the bulb will not light. And that's because sugar is a non-electrolyte. It does not conduct electricity. So non-electrolyte will be a compound which when in molten or aqueous form will not conduct electricity. So what are the differences between an electrolyte and a non-electrolyte? These will be obvious. An electrolyte conducts electricity in two forms, when it's in molten or aqueous form. Aqueous is the same as solution form, while a non-electrolyte, these ones do not conduct electricity in molten and solution form. Neither do they in solid form. Then lastly, an electrolyte will consist of free-moving oppositely charged ions. It must have some positive ions and some free-moving negative ions. So it contains ions. Always ions have to be charged, oppositely charged ions. However, under non-electrolytes, it will only consist of covalent molecules. And remember, covalent molecules are poor conductors of electricity, and as well, they don't contain free-moving ions. Obviously, the second point is the basis for the first point, but either way, there remain differences. Now we also have types of electrolytes. At least we have seen an electrolyte as a substance which when in molten or aqueous form, it will conduct electricity and it's decomposed by it. But we have those that are strong and those that are weak. So also we have grades in terms of electrolytes. So what is a strong electrolyte? This is a compound which ionizes or dissociates completely in dilute solution or in molten state into ions. So we are going to see what this means. First of all, it's a compound which ionizes, meaning it forms ions, or dissociates, which means, to associate is to somehow come together, but dissociate is kind of like decompose. So you do the reverse of associating, you kind of separate. So ionizes or separates. Completely, meaning almost all, if 3 people come together, 4 people come together to associate, and during dissociation all the 4 move away, that means it is complete dissociation in dilute solution or in molten state. So we shall always be dealing with solution or molten. That's why we have to add this part of, we can't say only in solution but also in molten state into the corresponding ions. So let's look at some examples of strong electrolytes, and hopefully we shall get the meaning of this simple definition of a strong electrolytes. Examples of strong electrolytes are shown below. These can be in form of salts, as long as they are in solution or molten form. They can be in form of acids, and they can be in form of alkali. So let us start with lead bromide. So lead bromide, if we heat it and then we melt it, it will be the molten form. Molten form. So when we pass electricity through molten lead bromide, let us put here L instead of solid to show that it's liquid. This electricity, actually, when we try to turn it into molten form, it will be split, or it will dissociate. Dissociate, now we are meaning to split into the corresponding ions, the lead 2 ions and bromide ions. So this is what we mean by a substance in molten form that will always dissociate or ionize fully. This is an ion, lead 2 ion. So we can say ionize or dissociate fully into the corresponding ions. This is the second ion, bromide. So this is an example of a strong electrolyte, because almost all of the atoms will try to dissociate or ionize completely into lead ions and bromide ions. Then we also have our common counterpart, sodium chloride, in aqueous form. That is to say, we have dissolved it in water. It will also ionize completely into sodium ions and chloride ions. So you can go back a few minutes back to this video and see the definition of a strong electrolyte, a substance which, when in molten or aqueous solution, we shall try to ionize or completely dissociate that given substance into its corresponding ions. We also have copper 2 sulfate, aqueous. It will also ionize into copper 2 ions and sulfate ions. So it is ionizing because it's forming ions. At the same time, it is dissociating because at first it was together, but now it is separating into the ions. We also have acids, hydrochloric acid, hydrogen ions, chloride ions. We can also have sulfuric acid into hydrogen ions, sulfate ions. So strong electrolytes will completely, now this word is important, completely ionize. So that is what is unique with strong. They completely ionize. And for us to explain the word completely, we have maybe to go into the version of concentration and we see what we mean by completely. Then under the alkali, we can have sodium hydroxide. It also ionizes or dissociates into the sodium ions and the hydroxide ions. But we shall get used to these terminologies as we proceed. Now we have a weak electrolyte. This will be a compound which ionizes or dissociates slightly. Now the difference between a weak and a strong will completely dissociate or ionize. However, weak electrolytes will slightly dissociate or ionize in dilute solutions or in molten state. So what are the examples of these compounds? We can also have acids, water, and alkali. When you look at this alkali, ammonium hydroxide, in aqueous form, that means there is some water, we shall slightly dissociate. So how do we notice slight dissociation? At least we try to represent it by this two-way arrow, showing that there is a forward reaction and there is also a backward reaction. So some of the ammonium hydroxide turns into ammonium ions and hydroxide ions, but in the due process some is turning back. So not all the ammonium hydroxide is split into the corresponding ions, the ammonium ion and the hydroxide ion, but some of it. So some will remain in aqueous form. That's what we mean by slightly dissociates. Not all the water will ionize into the corresponding ions. Some will remain as water molecules. However, for strong electrolytes, all the sodium chloride will break down or will dissociate into sodium ions and chloride ions. But for weak electrolytes, some will, some won't. For example, if you have, okay, let's leave that example. But let me hope for now at least you can tell the difference between a weak and a strong electrolyte. So what are the differences between weak and strong electrolytes? Obviously, strong electrolytes will ionize completely in aqueous or molten form, while weak electrolytes will ionize slightly. Strong electrolytes usually contain ions and no molecules. Ions are good at ionization. Yeah, that's where even the word ionization comes from. However, weak electrolytes, for them, they contain ions and molecules, for example, water. Then strong electrolytes, because they ionize completely, they will produce a higher current, thus causing a bulb to glow brightly. So because for them they can fully dissociate, fully ionize, then the electricity that will pass through will be high and the light will have to glow brightly. While for weak electrolytes, they don't completely ionize, yet it's the ions responsible for conducting electricity. As such, we shall produce a small current, causing the bulb to glow dimly, not as bright as the strong electrolyte. And then lastly, in case we are trying to measure something in terms of ammeter reading, the strong electrolyte will cause a very large deflection of the ammeter, obviously to show that we have more current, while a weak electrolyte will cause a small deflection in the ammeter to show that we have little current passing through. Some of these differences are obviously intertwined, but still they remain differences.